Chapter 3, Minerals. Minerals are the building blocks of rock. By definition, a mineral is naturally occurring, an inorganic solid, has an ordered internal molecular structure, a definite chemical composition. A rock, on the other hand, is a solid aggregate of minerals. So for example, this is our rock. It's the aggregate of at least 3 different minerals. The pink crystals here is our Feldspar mineral. Our black crystals are our hornblende mineral. And our semi-see-through gray minerals is our quartz. So definition of mineral again. Naturally occurring, generally inorganic. It's a solid substance, orderly crystalline structure, definite chemical composition. A rock is a solid mass of minerals or mineral-like matter that occurs naturally. Atoms are the building blocks of minerals. Now, an atom is the smallest particle of matter that cannot be chemically split. It's composed of protons, which have a positive charge, and neutrons with no charge. And these are surrounded by electrons. Each one has a -1 charge. Electrons exist as a cloud of negative charges surrounding the nucleus of protons and neutrons, called principal shells. The outermost shell contains valence electrons, which interact with other atoms to form chemical bonds. So here's a nice little diagram. Here's our nucleus of protons and neutrons, and electrons are circling around them, existing in a nice electron cloud. The atomic number, that's the number of protons in a nucleus of an atom, and determines the atom's chemical nature. Okay. An element is a group of the same kind of atoms. Approximately 90 natural elements and several synthesized in a laboratory exist. We can organize them in what's called a periodic table, so that those with similar properties line up. So periodic tables are categorizing of all the different atoms, so you can look up their features quickly. So here's a periodic table. So for example, each one of these blocks has an atomic number of an atom, its symbol of its element, its atomic weight, okay, and its name of its element. Okay, so here this H is hydrogen, is atomic number of 1, it's a weight of 1.0080, its name is hydrogen. Okay, here's aluminum, it's atomic number 13, capital A, lowercase l is its symbol, and it's 26.98 is its atomic weight. Okay, so we want to notice is that some of these are much heavier than others. Okay, so now chemical bonding. Now that's you form a compound by combining 2 or more elements, and to combine them they chemically bond. Okay, and they bond by transferring or sharing of electrons that allow each atom to attain full valence shell of electrons. Okay, so around the valence shell of electrons, okay, there's an octet rule. Atoms tend to gain, lose, or share electrons, so they're surrounded by 8 valence electrons. Okay, so that's a full shell is 8 electrons using the octet rule. Ionic bonding. Atoms gain or lose outermost valence electrons to form ions. Okay, so those are positively and negatively charged atoms. Ionic compounds consist of an orderly arrangement of oppositely charged ions. So an ionic bond is the attraction of oppositely charged ions to each other. So one example is halite, which is a mineral that we know as table salt, and it's made from sodium and chloride. So here we're showing a transfer of an electron from sodium, okay, which loses an electron and becomes positively charged. Yes, I think. Loses an electron, okay, which travels over to chlorine, okay, and that forms. So this one gains electron, okay, so they bond together to form NaCl, table salt. Okay, covalent bonds. Atoms share a pair of electrons. Okay, so as these 2 hydrogen atoms get closer and closer to each other, their outermost valence shell electrons start to be shared between them. Okay, this covalent bonding is a little bit stronger than ionic bonding. Now metallic bonding valence electrons are free to migrate amongst the atoms. This accounts for the high electrical conductivity of metals, especially copper. That's one example. Hybrid bonds. Many chemical bonds are actually hybrids. They exhibit some degree of electron sharing and some degree of electron transfer. Okay, precipitation of mineral matter. Ions dissolved in an aqueous solution reach saturation and start forming crystalline solids. A drop in temperature or water loss through evaporation can cause the ions to reach saturation and start to precipitate. Okay, so crystallization of molten rock. This is similar to water freezing. When magma is hot, the atoms are mobile. When the magma cools, the atoms slow down and begin to chemically combine. Okay, deposition as a rule of biological processes. Marine organisms secrete calcium carbonate, which we know as CaCO3. Okay, and so those form a mineral called calcite. Okay, so here's some examples of mineral formation. So here is geode with silicates dissolved in groundwater, precipitates, and it slowly crystallizes, okay, to form this quartz, okay, crystals here. As this magma cools, it'll crystallize and form rock. They have several minerals, okay. And this rock is made out of like calcite, possibly, that's been secreted from marine organisms. Primary diagnostic properties, okay. How can we tell one mineral from another? Well, minerals have physical properties that we can observe, and those are the primary diagnostic properties. So we can do some very easy tests, and we can identify many minerals that way without having to bring them into the laboratory. Okay, so we have several physical properties we're going to look at. One is luster. Okay, it's the appearance of a mineral in reflected light, or how that mineral reflects light. If it reflects it in a very shiny metal-like way, it's metallic luster. If it shines it in a non-metallic way, it might be vitreous or glassy, if it's reflecting like a piece of glass would, or dull or earthy, if it's not very shiny at all. It can be pearly luster, reflects light like a pearl would. Silky luster, it looks kind of silky, or it might be greasy, like how grease might reflect light. Okay, so here's an example using the mineral galena. Okay, and here it has a very nice metallic luster here. Now the sample on the left is a bit tarnished and it has a submetallic luster. Okay. Other optical properties, well, the ability to transmit light. A mineral that is opaque cannot transmit light through it. A translucent mineral, light can be transmitted, okay, so light shines through. But transparent, light and an image are visible through the sample, so you can actually look through it onto a piece of paper and see that there's writing on that piece of paper. Color, generally unreliable for mineral identification, mostly because weathering can occur and can change the color of that rock. Okay, but it's also highly variable due to impurities or slight changes in mineral chemistry. Quartz, slight change in mineral chemistry through impurity, you can have quartz in many different colors. Okay, here's some examples. So quartz, here's a smoky quartz, here's like a brown quartz, here's a white quartz, here's a purple quartz. Also fluorite, same scenario, many different colors. It's just slight variations usually due to impurities in the crystal. Streak is a better way of using color. It's the color of the mineral in its powdered form. Okay, not every mineral produces a streak when rubbed against a streak plate. The streak plate is a non-glazed porcelain plate. So you rub the mineral on it, and it may leave a scratch mark of powdered form of the mineral. And you look at the color of that. So here, pyrite, or fool's gold, is used to streak against a streak plate, and its streak is actually a black streak, even though the mineral is kind of sub-gold in color. Okay, crystal shape or habit. It's a characteristic shape of a crystal or aggregate of the crystals. Okay, some minerals will form a very fibrous crystal habit, like asbestos. Some crystals will form a bladed shape. Some may form cubic crystals. Okay, some may form banded forms. Okay, so there are many different crystal habits. Okay, mineral strength is how easily minerals break or deform under stress. Tenacity is the mineral's resistance to breaking or deforming. So brittle minerals, such as those with ionic bonds, will shatter into small pieces. Malleable minerals, just those with metallic bonds, are easily hammered out into different shapes. Like take a piece of copper. You can hammer it out to a long, thin sheet. You can stretch it out to a long, thin wire. Sectile minerals, such as gypsum and talc, can be cut into thin shavings. Elastic minerals, such as micas, will bend and snap back into their original shape. Hardness. It's the resistance of a mineral to abrasion or scratching. All minerals are compared to a standard scale called Mohs scale of hardness. Okay, so a Mohs scale of hardness is not a linear scale, okay, but there are 10 steps on it. So the real hard ones are like 10 and 9 and 8, but each one is harder than a lot harder than the one previous. Okay, so these 10 minerals are index minerals, so to speak, for Mohs scale. Talc is our softest at 1, gypsum's at 2, calcite at 3, fluorite at 4. Let's see, quartz is at 7, corundum's at 9, diamond's the hardest we know, and it's at 10. So we compare our minerals with simple tools when we're in the field. So we don't have to carry a diamond and corundum crystal, topaz, quartz, all those in our pocket. We can use our fingernail. Our fingernail should be about 2.5 on the hardness scale. So that should be, with the fingernail, we should be able to scratch the gypsum or talc. We have a copper penny, a real copper penny. So these are not the, so we're talking about the older pennies that have more copper than our 1990s and more recent pennies. They have a hardness of 3.5. They can scratch calcite as well as gypsum and talc. A wire nail is a 4.5, and it can scratch fluorite. Okay, a glass and knife blade is about 5.5, so quartz can scratch glass still. Okay. Now streak plate, which is that porcelain plate, well, that's at 6.5. Okay. So you can use these common objects to figure out the relative hardness of one mineral versus another. Now cleavage is the tendency to break along planes of weak bounding. This produces flat, smooth surfaces, can sometimes be a little shiny. So we describe it by the number of planes and the angles between adjacent planes and the resulting geometric shapes. Okay, so here we're going to look at D first. So here we have a chunk of halite, or rock salt, and this is cubic cleavage because it has 3 planes of cleavage at 90 degrees. So if you compare the top and the bottom are parallel to each other, that's plane 1, and then left side and right side are parallel to each other, so that's plane 2, and then the front and the back are parallel to each other, that's plane 3. So it's 3 planes of cleavage at 90 degrees angle. It's kind of like a 6-sided die. Okay. Now cleavage that's in 3 directions, not at 90 degrees. Calcite. Okay, so one plane is actually these planes are not at 90 degrees, so they look more like a shoebox. Okay, fluorite has 4 planes of cleavage, and so in 4 different directions there's cleavage, and it's kind of like an 8-sided die if you play role-playing games with dice. Let's see. Here's an example of hornblende is cleavage in 2 directions, so between the top and the bottom, and the right and the left side, but not between the front and the back. And they're at 60 degrees, well, 60 degrees and 120 degrees, so not 90 degrees. So, okay, so that's going to be your hornblende. Then your cleavage in 2 directions at 90 degrees, so your feldspars. So you see this nice 90 degree angle here, rather than the 120 here. Okay, so we have plenty of cleavage through here, plenty of cleavage through here. Now micas. These micas, muscovite and biotite, you can actually peel this mineral apart in layers, like peeling pieces of paper off a notepad. This has cleavage in only 1 direction. Okay, so here's another example of our mica. So it's a silicate. So here's our 2 silicate layers, and you either use a knife blade or sometimes your fingernail, and you can actually just peel these layers apart because there's a very weak bond between the layers. It's this ionic bond. Within each layer there's covalent bonding that's much stronger. Pyrite. You may see cubic cleavage, and you might see dodecahedron cleavage. Okay, and sometimes pyrite gets confused. It wants to form a cube, then wants to form a dodecahedron, then wants to form a cube, and it causes it to form these lines called striations. You'll see striations on one of the feldspars, and you'll see striations also on quartz sometimes. But this helps you identify pyrite versus, let's say, galena, which is silvery in color, and this one's golden color, but in low lighting you may not be able to see the difference. But the striations will let you know that it's actually pyrite, not galena. Okay, so fracture is when you don't have cleavage, so that's when a mineral breaks in irregular fractures, or it's just a rough edge, or might be conchoidal fractures, that circular fracture you might see when you break glass, splintery fracture into splinters, or fibrous fractures, kind of like asbestos peeling apart. So here's an irregular fracture. Here's a conchoidal fracture. Okay, density. Density is defined as a mass per unit volume. Okay, so the more mass packed into that mineral, the heavier it's going to feel. Okay. Now, specific gravity is the ratio of the weight of a mineral to the weight of an equal volume of water. Okay. So you take like 1 cubic centimeter of mineral, and you weigh it, and then you weigh 1 cubic centimeter of water, and you weigh it, and you divide the mineral divided by the water, and its weight, and you end up with a number typically between 2 and 3. So the minerals with a lighter density and specific gravity are closer to the 2s, and the heavier ones are going to be 3 or more. Like some of the minerals we'll look at have specific gravity of 3.3. Other properties or special properties. Some minerals have a taste. Okay, halite tastes like salt. Might have a certain feel to it. Talc feels soapy, and graphite feels greasy. Magnetism. Magnetite is magnetic. You can pick it up with a magnet. Okay, lodestone is a natural magnet. Other properties besides magnetism, some minerals react to hydrochloric acid. Okay, so like calcite, you put hydrochloric acid on it, and it's going to start forming these carbon dioxide bubbles. Some are malleable. You can hammer them out nice and thin, like copper. Some will have a taste, like the halite we mentioned. Smell, like sulfur may have some smell to it, like rotten eggs. Some minerals can be elastic. Some have double refraction, which is my favorite property, because that calcite has the 3 planes of cleavage, not at 90 degrees, so this top face is pushed over versus the lower face, okay? And since sometimes it's very transparent, a really good crystal, you can see right through to the writing on the paper, but that the light that you're looking through gets refracted twice. It gets, well, actually 4 times, going in, going down and out onto the paper, and reflecting back up. It gets bent, and it gets bent again by the top face. So you see double. That's called double refraction. Okay, so that's an optical special property. Let's see. Okay, so we talked about those. Okay, all mineral samples are crystal or crystalline solids. Any natural solid with orderly repeating internal structure. Okay, so now our mineral structures, we have unit cells. That's the atomic arrangement that results in the basic building blocks of a mineral crystal. Minerals can be constructed of the same unit cells and have different external forms. Okay, so minerals with a cubic unit cell include fluorite. Crystals can be cubes. Magnetite, the crystals can be octahedrons of 8 sides. Garnets, those crystals can form dodecahedrons, yet they still have a cubic unit cell. Okay, so basically, the unit cell forms basically a cube, but they put together differently. So the fluorite will form cubes. Okay, the magnetite will form octahedrons, and the garnet form a 12-sided shape called a dodecahedron. Mineral structures, Steno's law, or law of consistency of interfacial angles, regardless of the crystal size. The angles between equivalent crystal faces of the same mineral are always the same. Okay, that helps get us those different degrees, angles. Compositional variations of minerals. Ions of similar size can substitute for one another without disrupting the mineral's internal framework. Okay, so there's a mineral called olivine. Okay, and it has basically, it's formed out of the silicon oxygen tetrahedra plus an iron or plus a magnesium, as these will swap out between each other kind of randomly, but it still is olivine. Other minerals have trace variations in their chemical compositions, including quartz and fluorite, and that can cause significant changes to its mineral color. Structural variations in minerals, or polymorphs, minerals with the same composition but different crystalline structures. Examples are diamond and graphite. Transferring one polymorph for another is called phase change. Diamond and graphite are just form of carbon. Okay, so the graphite is formed in sheets of circular bonded carbon ions. Diamond, the carbon connects covalent bonds in every direction it possibly can. So here's our diagram. So here's our graphite, where these sheets of carbon atoms with covalent bonds that are weakly bonded ionically to each other. Okay? In a diamond, the carbon atoms are bonded complexly with covalent bonds in every direction possible, forming a very strong mineral. So it's like our weakest to our strongest. Nearly 4,000 minerals have been named. Okay? Now, the rock-forming minerals, though, there are only a few dozen. And common minerals that make up most of the rocks of the Earth's crust. They are composed mainly of 8 elements, make up most of the continental crust. Those 8 elements are oxygen, almost half, silicon, almost a third, potassium is 2.5%, magnesium 2.1%, sodium is almost 3%, calcium is 3.6%, 8% is aluminum, and the rest is only 1.5% of all the rock out there in our continental crust. So how do we classify them? Well, a collection of specimens that exhibit similar internal structure and chemical compositions are called mineral species. Mineral species are further divided into mineral varieties. So examples of varieties are quartz. You may have a smoky quartz that has traces of aluminum. You may have an amethyst, which has traces amounts of iron. Mineral species are assigned to mineral classes. So those classes are silicates, carbonates, halites, sulfates. They're all different mineral classes. The silicate minerals are the most common minerals. They account for over 90% of Earth's crust. Silicon and oxygen make up the basic building blocks of silicate minerals. Non-silicate minerals are not as common as the silicates, but are very important economically. So all silicate minerals include oxygen and silicon, the two most abundant elements in Earth's crust. Okay, so these form these silicon and oxygen tetrahedrons. Okay, these four-sided pyramid-shaped building blocks with 4 oxygen ions surrounding a much smaller silicon ion. The single tetrahedra are linked together to form various structures. Okay, so here is a single tetrahedra of silicon and oxygen. So silicon's in the middle, and then there are 4 oxygens around it. Okay, minerals that have an independent tetrahedra. Okay, oxygen ions are bonded with positive ions such as magnesium, iron, or calcium. Examples include olivine and garnet. They form very hard, dense, equidimensional crystals that lack cleavage. Minerals with chain or sheet structures, okay, polymerization, the SiO4 tetrahedra can link to one another in a variety of configurations. This accounts for high variety of silicate minerals. The tetrahedra can form single chains, double chains, and sheet structures. Some oxygen ions are shared between the tetrahedra. And some minerals have a 3-dimensional framework. All oxygen ions are shared between the tetrahedra. Examples are quartz and the feldspars. Okay, so here we go. So our independent tetrahedra, they look like. A single chain, tetrahedras are connected by 1 oxygen from its neighbor. Okay, and from the sides what they look like. A double chain, we have 2 single chains connected. So each tetrahedra is connected by 2 oxygens from 2 different tetrahedras. The sheet structure, basically tetrahedras are forming rings, okay, in a sheet form. Okay, so there's a side view of the end view of the double chain, end view of a sheet. 3-dimensional frameworks with tetrahedra are bonding with another tetrahedra at each point where there's an oxygen. So joining the silicate structures, most silicate minerals have a net negative charge, except for quartz. Metal ions are required to balance that charge. Okay, so they have positive charge. These positive ions bond with the unshared oxygen ions in the tetrahedra. The most common ones are iron 2+, magnesium 2+, potassium, sodium, aluminum 3+, calcium 2+. Okay. Covalent silicon and oxygen bonds are typically stronger than the ionic bonds of the silicate structure. This controls the cleavage and hardness of minerals. Examples: quartz is a 3-dimensional framework that's very hard and lacks cleavage. Talc is a sheet structure framework bonded with magnesium ions, and it's a very soft mineral. The feldspars are the most common silicate group, making up more than 50% of Earth's crust. Quartz is the second most abundant mineral in the continental crust and the only common mineral made completely of silicon and oxygen. So here's our common silicate mineral chart. So here's our olivine group. It has a single tetrahedra, forms these small little equidimensional crystals. Our pyroxene groups include augite, so it's a single chain. And the single chains are kind of narrow, so they're able to have two planes of cleavage at 90 degrees. Okay. Now our double chain ones are amphibole group or hornblende. So because this chain is wider, they tend to form cleavage planes at 60 and 120 degrees. Then we have our sheet structure silicates, or micas, our biotite, and our muscovite. Our biotites are dark silicate. That's going to have our heavier minerals in it, the magnesium, iron. Let's see, and then our lighter silicate one is our muscovite. And then our complex three-dimensional network is our feldspars, which is our potassium feldspar, and our plagioclase feldspar. And then here's our quartz. Okay. So now we can divide our silicates into two groups based on density, basically, our light silicates and our dark silicates. So our light or non-ferromagnesium silicates are generally light in color, have a specific gravity of approximately 2.7, contain varying amounts of aluminum, potassium, calcium, and sodium. Not very much iron or magnesium, if any. The feldspar group is the most common mineral group in this grouping, forms under a wide range of temperatures and pressures, exhibits two directions of perfect cleavage at 90 degrees. Most common members are the orthoclase, or potassium feldspar, and our plagioclase, or sodium and calcium feldspar. So here's our potassium feldspar. Okay, this is a crystal. This is showing its cleavage. Okay, so it's 2 planes at 90 degrees. Our plagioclase feldspar, here's albite version, and here's labradorite. And this one kind of shows its striations. Sometimes you can tell your plagioclase from your orthoclase, because your plagioclase will have striations, those lines in it. Quartz is the only common silicate composed entirely of oxygen and silicon. It's hard and resistant to weathering. Its conchoidal fracture often forms hexagonal crystals and colored by impurities, which are various ions. Muscovite, common member of the mica family, excellent cleavage in one direction, which forms thin sheets that are clear. Okay, in the Middle Ages, they used muscovite as glass in the Middle Ages. You can pull the sheets apart. It produces the glimmering brilliance often seen in beach sand. Clay minerals. Clay is a general term used to describe a variety of complex minerals that have a sheet structure. Clay makes up a large percentage of the soil. Most originate as products of chemical weathering. Kaolinite is a common clay mineral used to manufacture fine china. So these are actually minerals that are formed from like decomposition of other silicate minerals. Now the dark or ferromagnesium silicates contain iron and or magnesium in the structure. So these are heavier, dark minerals, the heavier, darker ions in them. So they're generally dark in color. Have a specific gravity between 3.2 and 3.6. The olivine group, or high temperature silicates, black to green in color, glassy luster and conchoidal fracture, form small rounded crystals. The pyroxene group, important components of dark colored igneous rocks. Augite is the most common mineral in the pyroxene group, black in color, two distinctive cleavages at nearly 90 degrees. It's a dominant mineral in basalt. Amphibole group, hornblende is the most common mineral in this group. Two perfect cleavages existing of angles of 120 and 60 degrees. Here is a picture of some augite, and here's a picture of some hornblende. Okay, so the cleavage angles for augite and hornblende. Remember, the augite pyroxene group is that single chain. So those chains kind of stack together closer, so you're able to get that 90 degrees cleavage. The double chain is a wider form, so you end up having angles of cleavage of 120, and of course because angles have to complement each other, you have 120 and 60 degree angles, your hornblendes. Dark silicates also include biotite. This is your dark iron-rich member of the mica family, excellent cleavage in one direction, you peel apart in sheets. And garnet, composed of individual tetrahedral linked by metallic ions, similar to olivine. It's a glassy luster and conchoidal fracture. Here's a picture of biotite and muscovite. Important non-silicate minerals. Divided into groups based on the negatively charged ion or complex ion that the members have in common. These make up only 8% of Earth's crust. So our carbonates have CO2. Okay, so these are calcites and our dolomites. Okay, this forms Portland cement and lime. Halites, which have our chlorine, And so these form our halite, our fluorite, our sylvite. Okay, these are used for salt or fertilizer or steel making. Oxides, -2 oxygen, form our hematite or magnetite or corundum, and ice. Yes, ice and is water in its solid form, and that is a mineral. Sulfides, S-2, like galena, sphalerite, pyrite, chalcopyrite, and cinnabar. So most of these are ores. Like galena is an ore of lead, sphalerite is an ore of zinc, pyrite is for sulfuric acid production, chalcopyrite is an ore of copper, and cinnabar is an ore of mercury. Sulfates have the SO-2, well, SO4 -2, gypsum, anhydrite, and barite. These are barite's a drilling mud, so it's a lubricant for drilling. Gypsum and anhydrite used in making plaster. And then our native elements are just single elements. So we have, you can find gold, you can find copper, diamonds, sulfur, graphite, silver, and platinum. And they have their various uses. So carbonite's composed of the carbonate ion, CO3, and it's -2 negatively charged, and that combines with a positive ion. Two most common carbonates are calcite, CaCO3, and dolomite, CaMgCO3, the two of those. Okay, primary constituents in limestone and dolostone. Okay, many non-silicate minerals have economic value. Example, halite is mined for salt. Gypsum is used in making building materials. Hematite and magnetite is mined for iron ore, and native elements, gold, silver, and diamonds, well, you know what we use those for. Okay, so here's some pictures of some of these important minerals: calcite, dolomite, halite, gypsum, hematite, magnetite, or iron ores, galena, chalcopyrite, and fluorite. Now, magnetite and hematite are both iron oxides, and yet hematite can be red, it can be black, it can be shiny, it can be dull, but it will have if you took a streak of hematite, it would have a red-black or brownish, like reddy brown streak to it. Magnetite's typically black, and they'll have a black streak. It's also magnetic. There's a picture of an underground halite mine or salt mine. You know, of mines I know of, this most lightest area is kind of underground mine you can be in.